Hi everybody and welcome to this very first video on my new channel. My name is Judy and today we'll be speaking about something called Solomon's knot. Actually, just a couple of weeks ago, I had already recorded an introduction to this video.
And it's Easter coming up. And because of that, my dad was asked to sing in church. So he brought home this book. And I couldn't believe my eyes. As a kid, I was an altar boy. Altar girl? Whatever. And I used to carry this exact book around for the priest. Nostalgia. And I was always mesmerized by the pattern on it.
As it turns out, I was not the only one mesmerized by this pattern. But shortly after recording this introduction, I went to Italy and I got to visit some ancient Roman mosaics in both Aquileia and Grado. And what did I see? As already mentioned, this pattern is called Solomon's knot, most probably due to the fact that it can be found in ancient synagogues and was therefore associated with King Solomon. It actually appears in a variety of cultures and therefore also carries with it a variety of different meanings. For example, as a Celtic symbol, the focus lies on the fact that there are two intertwined loops and therefore it symbolizes love. As an ancient Roman symbol, the focus was on the fact that there is no beginning and no end to it, so it symbolizes eternity. And here's what I found interesting about it.
And I was always mesmerized by the pattern on it. My eyes would trace the lines, and soon I would realize that this entire pattern is made up of exactly one loop. Now, that made my mind wander a little bit.
Now we have already seen two contrasting facts about this pattern. On the one hand, it may be made up of multiple loops. For example, here 2 loops, 3 loops, or even 4 loops. On the other hand, we have a pattern made up of exactly 1 loop. Now, back in the day, I already had a suspicion when this might happen.
Now, that made my mind wander a little bit. You may notice that on this side, there are 9 corners, and on top, there are 7 corners. So I was thinking, what if I changed the number of corners? Would it still be 1 loop? And soon I had convinced myself that as long as the number of corners on this side and the number of corners on this side do not have a common divisor, then yes, it would be exactly 1 loop. But if they have a common divisor, there would be multiple loops. Why is that? I had no idea at the time.
But is this really the case, or was it just my intuition? Is it true, and can we prove it? Today we'll dig deeper into this.
First, a little disclaimer. For those of you who know what knot theory is, this pattern is not a knot in a mathematical sense. But Solomon's knot for me is easier to pronounce than Solomon's guyot, so I will keep referring to it as Solomon's knot in this video, just as long as we understand that we can't apply any knot theory to it. Let us start by discovering how Solomon's knot is actually constructed. Now, when it comes to the beautiful pattern that you see in the mosaics, there is a lot of focus on how big each of the loops are, where the crossings are happening, and so on. Since this will not be important in determining how many loops a given Solomon's knot consists of, we will not pay any attention to it. If you're interested, there's actually a lovely video by Roman Mosaic Workshop Limited teaching you about all the artistic detailing. The link to this video will be in the description below. But for this video, we will not worry about the line crossings and just view it as a grid. And we will also make the rounded corners a bit sharper to help with the construction. Alright then, how would we construct the simplified pattern? Notice that in this particular image, there are 4 pointy bits on top and bottom, and 6 pointy bits on the sides. Therefore, we say that this is a 6x4 Solomon's knot. In order to draw this pattern, we start with a 6x4 grid. We mark the midpoints of each of the border segments, and then we just start connecting these midpoints diagonally. First this way, and then the other direction. And voila, now we have the original knot. Okay, minus the pretty lacing, but as we said, that's not important here. If you looked closely, you may have already noticed that in the 6x4 knot, there are exactly 2 loops. So why is that? To understand this, it actually helps to not consider the construction I've shown you thus far, but rather think of an alternative construction. And don't worry, this was not all for nothing. We will still need this construction I've shown you up to now again later. So, instead of connecting midpoints of line segments, I want you to view each of the pointed bits as reflections. For example, I don't want you to think of this line here and this line there as different lines, but as the same line reflected about this axis. In that sense, the loop in red is just one big diagonal loop, but reflected 3 times. Here, here, and here. Now the question becomes, how many folds do I have to do before I can have a closed loop? To answer this question, we need one more observation. When we folded the red loop in the 6x4 pattern, we did this in a very particular order. But as it turns out, the order of folding, and hence the order of reflection, doesn't matter. What this means is that if we fold in any other order, and there are actually 6 possible ways of doing that, we get the same result. In particular, if we choose to fold this way, then at an intermediate step, we end up with a zigzag pattern, where each of the zigs and zags corresponds to a left-right reflection. And since each of the left-right reflections happened after exactly 4 steps, each zig and zag happens after exactly 4 steps. And by definition, that is the base length of the Solomon's knot we're trying to create here. Remember, we folded after 4 steps to create a 6x4 pattern. Now I've drawn the zigzag pattern again on a separate piece of paper just to make it a little bit easier to see without all the foldings happening. I've also drawn it a little bit longer here because I want to get a point across. You will see shortly. In order to arrive at the red loop in the 6x4 knot, we have to fold this pattern after 6 steps. And indeed, the loop is closed. However, if we fold after only 5 steps, the loop is not closed after just 1 fold. We actually need 2 additional folds. Here. And here. To obtain a closed loop. And in this case, we actually end up with the full 5x4 Solomon's knot. To understand this, let's look at the unfolded pattern again. When we fold the zigzag pattern, we are determining the side length of Solomon's knot. This is why folding after 5 steps yields the 5x4 knot, while folding after 6 steps yields the red loop in the 6x4 knot. And therefore, we end up with a closed loop whenever the zigzag, the base length of the pattern, coincides with the folding, the side length of the pattern. The first time this happens will be at the smallest common multiple, the SCM of the 2 lengths. We're now almost at the point where we can determine how many disjoint closed loops are in a given Solomon's knot. We just need to define one more quantity. Now we want to define the area of the loop as the number of squares in this grid that we can fill with a full diamond, just like this one, only using segments of the loop. But wait, currently there are no diamonds in this grid. Well, let us split up the loop into line segments, like this, and then just rearrange the red and green line segments a little bit to obtain a whole bunch of diamonds. And I'll leave it up to you to think about why it is always possible to split up a closed loop of this kind into diamonds without having some leftover pieces. And hint, it is necessary that the loop is actually closed. Anyways, after making these diamonds out of the closed loop, we see that by our definition, the area of the loop is the same as the base length of this grid, which we already identified as the smallest common multiple of the side length of the Solomon's knot. Now we need to use a little bit of math here. Namely, we use the fact that the smallest common multiple of any two numbers is proportional to the product of these two numbers up to a factor. And this proportionality factor is the greatest common divisor, the GCD, of the two numbers. You can pause the video here if you want to go through the proof of this relation in detail, but the idea is to construct the smallest common multiple of A and B from an already known common multiple of A and B, namely the product of A and B. Now, to get the smallest common multiple from this product, we want to make the product smaller by dividing it through some factor k. Now, to be guaranteed to still get a multiple of A and B, this dividing factor k better also divides A and B individually. And the largest number that fulfills this property is the greatest common divisor of A and B, thus giving us the smallest common multiple of A and B. Okay, great, but how does this help us exactly? Well, we define the area of a closed loop as the number of diamonds we can form from the line segments. If we now go back to the original construction method of Solomon's knot, see, I promised you that we would need it again. We see that it is made up of a whole bunch of such diamonds. So, analogously to the area of the loop, we define the area of the knot as the number of squares filled with these diamonds. And as per the construction, this number is just the product of the side length and the base length. And now we have it. If this product of side and base length is the area of the whole knot, and the smallest common multiple is the area of the closed loop in a knot, then we end up with exactly one loop if the greatest common divisor of the side length and the base length is 1, because then these two quantities are the same. And we end up with multiple loops if the greatest common divisor of the side length and the base length is greater than 1. In fact, we end up with whatever the greatest common divisor is, many loops. So great, my intuition was right. Yay!
So now we know Solomon's knot is made up of multiple loops if the two side lengths have a common divisor, and of exactly one loop if their greatest common divisor is 1. And now, when do you ever need to know this? Well, never. Presumably you will never need to know this. But if you want to know this, this teaches you something about yourself. Maybe it teaches you that you found a new hobby, that you enjoy solving these kinds of riddles. Maybe it teaches you that you found a new passion, that you want mathematics to play a bigger role in your life. Or maybe it teaches you that math is about more than just calculations. Math is the language of nature, and therefore it also allows for the poetry of nature. Thank you for watching. Bye.